Hello, do we have this problem from Putnam 1994? I think it's a really good weekender. It's an elegant problem. You just need to find the approach. So we have to find real number c such that there's a straight line crossing this polynomial at 4 points. So let's begin by saying that x4 plus 9x cubed plus x squared plus 9x plus 4 equals, and now we're gonna write the standard line equation, ax plus b. What we're gonna do next is move it here and say x to the 4 power plus 9x cubed plus cx squared, and plus now we're gonna do this stuff with the dx term. 9 plus a is a coefficient now, and now the constant part, 4 plus b equals 0. Now the only thing we need to do is find under what value c there's a pair of a and b such that this polynomial will have 4 solutions. So let's go ahead and try to make a graph, not for this expression overall, but just 4-degree polynomials. Let's see how they could behave theoretically. So theoretically, first of all, we could have something like a parabola-like structure, something like this, something like this, something like this. You know the drill. So parabola-like structures, that's one, what we have. And for two, we could have something like this, or something like this. Okay, I have mentioned that already. So what we have here is this structure, this nearly ideal parabola-like structure, which is just parabola squared, and this version of parabola with inflection points. So the interesting thing about all of this is we can easily see that the version of parabola with the inflection points were to draw a straight line, y equals some constant, like this, then you can see that at all points it's at most 2 solutions. Even here, when one of the inflection points is raised, you can't really squeeze out anything. Even if the inflection points coincide like this, there's still gonna be one root here. So what are we gonna do? Here, it's either 1 at the vertex or 2 at the other side. So really, the only formation that does interest us is polynomial 4th degree with 3 extremums, 1 maxima, and 1 and 2 minima. So, thing is, you would argue that, well, what if it's above the graph? What if it's above the graph? What if it never touches it? What if I'm picky like that, right? And thing that you can do is go ahead. Let's say that y coordinate here is y1, y coordinate here is y2, y coordinate here is y3. Let's say that y2 is greater than y1 and y3, and let's say that y4 is the greater one out of y1 and y3. Now we can pick any point c between y4 and y2. Let's take it here, for example. And what we can do is, if this graph is represented by p of x, then we can define p2 of x and say that it's p of x minus c. And you will ask me, how does this work? How can we just go ahead and add a constant term? And the nice thing about this is we have these two absolutely modifiable pairs of variables. If we need to find polynomials like this, then we can go ahead and say that we can change the variable b. It's not a problem. We can always alter it. We can say that there is b2, and that's just b minus c, and that's it. So we can assume that as long as we can find a polynomial with 3 extremums, then it's gonna have 3 solutions. It's not a problem for us at all. So let's go ahead and work on that. We're gonna find the derivative of this polynomial. That's gonna be 4x cubed plus 27x squared plus 2cx plus 9 plus a. And now the funny part here is that the b term vaporized. That means that it doesn't affect the extremum part, so we can safely modify it without modifying the polynomial function. It is going to be not the polynomial function itself, the presence of extremums is going to be independent. So now we need to work with this. Now, a polynomial of 4th degree can have 4 inflection points like this one. Not 4, I mean 3. So what we really need to do is just show that this has 3 solutions, then they're guaranteed to be extremums and not inflection points. So let's go ahead and do that. Let's show that this expression has 3 roots. And now thing is, we can go ahead and do the absolute same approach as for the 4th degree polynomial. If we were to observe different cubics, then the only one where you can't draw a straight line like this parallel to the x-axis is gonna be one with an inflection point. All the other ones are not going to have an inflection point. Instead, they would have 2 extremums. Now let's show that. Let's find the second derivative of the 4th degree polynomial, or well, the derivative of this cubic. We're gonna have is 12x squared plus 54x plus 2c. Notice how this term vaporized again. It's important because that means that we can move around this cubic. So if it has 2 extremums, we can just take this point C and move it down. It's not a problem. So let's look at this, and this is either gonna have one solution for d equals 0. This is the inflection point solution because, well, this thing can have 1 extremum. 2 solutions. This is for discriminant greater than 0, and 0 solutions. This is for discriminant less than 0. Now, the only one that interests us is the one with 2 extremums. So, discriminant greater than 0. And then, we don't really care if it's above the graph, we can just move it with the A term. Okay, so let's find when the discriminant is going to be greater than 0. To find the discriminant, we square 54, and we subtract 4 times 2 times 12 times c. That's going to be 96c, greater than 0. Now let's factorize 54 and 96. 54 is gonna be 27 times 2, so just 3 cubed times 2. And 96, I mean, we just express it as a product of 12, 2, and 4. 12 is 12 squared times 3. Have 2 here and also 4. So that's gonna be 2 to the 5th times 3. Okay, now the LCM is gonna be equal to... Okay, wait a second, not sure if this part is correct. 32 times 3, okay, checks out. So, okay, wait, no, I'm really suspicious of this. This doesn't seem right. I'm suspecting myself. Oh, wait, no. Okay, it's correct. I forgot that we have 54 squared here. So what we really need to look for LCM of is 54 squared and 96. Now, 54 squared is gonna be 3 to the 6th power times 2 squared. The LCM is gonna be 12. So we can divide this by 12 and get 3 to the 5th times... Now we have 2 squared here, 4 here, so times nothing, minus 96 is 2 to the 5th times 3. So if we were to divide it, it's going to be 2 to the 3rd c greater than 0. And we just move c to the other side. We have 3 to the 5th greater than 2 cubed c, and c is less than 3 to the 5th over 2 cubed. That's gonna be 143 over 8. Or we can write this down as 30 plus 3 over 8. And 3 over 8 is gonna be 125 over 1000 times 3. That's gonna be 375. So what we have essentially proven right now is as long as c is less than 30.365, the 4th degree polynomial over here will have a straight line that intersects it at the 4 points. Thank you for watching. I hope you liked it. Bye.